Okay, so I'm going to talk a little bit about the ionosphere-thermosphere research we have carried out at University of Oulu in Finland, together with my team members and other co-authors. How can I change the slide?
Okay.
Okay. And the outline of my talk is here. So first I want to give a little bit background to the ionosphere-thermosphere system and geomagnetic storms. And then I briefly introduce some of the most important instruments we have used in our studies. And then I will go to some of our recent studies carried out under this ESA's 4D ionosphere joint project. Then a little bit about this Mother's Day superstorm. And finally, one study about ionospheric cusp dynamics. And then I try to summarize some of the open questions we should study and some future prospects. So first, ionosphere-thermosphere. So in this plot, oops, okay, I perhaps should not use this. Oh, not wrong direction. Okay, on this plot, on this left-hand side, you can see a schematics of the ionosphere. And we typically talk about ionosphere between 70 and 1,000 kilometer altitudes. And that is a region where you also can find aurora borealis. That is also where you have the International Space Station, several ionospheric satellites. And then the neutral atmosphere at these altitudes, that is called the thermosphere. And these ions and neutrals, they have complex interactions. So we could say that ionosphere is the region where the space meets the atmosphere. A few words about geomagnetic storms and substorms. And this animation is actually describing what is happening to Earth's magnetic field and magnetosphere during a substorm. And the solar wind is coming in this animation from the left-hand side, and then it interacts with the Earth's geomagnetic field. And I will not go to the details, but you can see that many things are happening there. And the typical timescale for one substorm is about 3 hours. And the other concept is a geomagnetic storm. And typically during one storm, we can have several substorms. And storms can last for hours, from hours to days. And one very important property of the storm is that the ring current in the magnetosphere is greatly intensified during storms. You all obviously know quite well the Swarm satellites, but I still repeat some of the basics. So they are polar orbiting satellites between 400 to 500 kilometer altitudes. And they carry quite many kind of instruments. And in our studies, we have utilized most of them. So there are these magnetometers. There is the thermal ion imager, which gives us the electric field. There are Langmuir probes. There are GPS receivers and accelerometers that can provide estimates of the neutral density. And in general, these satellites, polar orbiting satellites, are nice because they provide us with very good latitudinal coverage of things. But then if you want to have information above a certain latitude, you get that only once per orbit, which is roughly 1.5 hours. Then we go to ground-based instruments. So one very important instrumentation for us are incoherent scatter radars. And there on the left-hand side, you can see the ASCAT Svalbard radars. And here on the right-hand side is the ASCAT 3D radar, which is currently being built in northern Norway, also in Finland and Sweden. And additional ground-based instruments are, of course, magnetometers, auroral cameras, fabric interferometers, and so on. And the benefit for ground-based instrumentation is that they provide a continuous time series over a given location. But of course, their field of view is very limited. Let's now go to some of the results. So Joule heating is one of the very basic important parameters. So it describes the electromagnetic energy that is coming from the magnetosphere to the ionosphere. And in our team, Heikki Vanhamäki has developed a nice method to estimate the ionospheric global Joule heating based on measurements by the network of supermag magnetometers, superdown radars, which provide the electric fields, and iridium satellite magnetometer measurements, which are also globally covering the Earth. And then you can see these results of Joule heating changes. This is a statistical map, so-called superposed epoch analysis. And you can see on the rim are the magnetic local times, and then you can have latitudes. Noon is on the top, midnight is in the bottom. And now the time series is starting, so there is very little Joule heating before the storm onset, but then as the storm starts, the Joule heating is going to have higher values, and typically we have higher values within the outer oval, also to some extent in the polar cap. And here I have two panels. So this upper panel is the integrated Joule heating in the northern hemisphere, and the lower panel is the analysis of the neutral density changes at about 450 kilometer altitudes based on Swarm and Grace measurements. And as the Joule heating is getting up, also the density enhancements start to be visible in the data, and the statistical median is over 100% increased compared to the quiet level baseline. Then I go to the superstorm. So this May 2024 event that was driven by the coronal mass ejection. You can see the solar surface. There was an active region, so very big group of sunspots, and around those several coronal mass ejections were launched, and they hit the Earth's magnetosphere, ionosphere, caused the storm effects. And I here just focus on some of the high latitude observations. So these color panels here, they show the ASCAT Svalbard measurements. So the bottom panel shows the electron density, and then the electron density change. And here are several days. So the storm onset is here. And after the storm onset, practically the ionosphere was wiped out. The electron densities became very small. And during the same time, we had clear enhancements in ion temperature. And those ion temperature enhancements are related to increased Joule heating, increased electromagnetic energy input to the ionosphere. And the physical mechanism of this wiping out of the electron density is in the fact that the recombination speed or recombination rate of ions is greatly enhanced. Then still during this superstorm here is the total electron content variation. So actually it is the actual total electron content shown. And this movie will soon start again. And in the beginning of the storm, there should be polar cap patches going over the polar cap. Now they come soon. Now they go over the polar cap. After that, there will be, they still go But after that, there is a lot of this blue color, and this is the depletion in total electron content that we also saw with the Svalbard radar. Okay. What else happened? So again, some swarm observations. So this panel shows the swarm A neutral mass density measurements, and after the storm onset, we saw a very clear enhancement in mass densities lasting for about 1 day. The top panel shows the time satellite measurements, and basically it is telling us that the N2 molecules, their relative abundance to O is increased. So this is again related to the upwelling of the thermosphere. And maybe one more thing, so this paper has just come out, is that we show that the estimated Joule heating rate in the northern hemisphere was exceeding 1 terawatt during this event. And the last thing I wanted to tell about is a CASP study using SWARM satellite and again EISCAT's radar observations. And first, why CASP is interesting is the figure on the left-hand side. So that is the region where the solar wind particles have a direct entry to the Earth's ionosphere. And those feed lines map to very high latitudes on the day side. And often the EISCAT Svalbard radar on the day side is within the CASP region, but not always, because this CASP location varies in latitude depending on the IMF conditions. And during this specific event, there was also the Svalbard swarm orbit, swarm overpass over the CASP, and I will show some of the measurements by the SWARM satellite. And here again, I have a plot with quite many panels. So let's start from the top panel. So this is the, first of all, this is latitude, and the parameter shown here is electron temperature. So we have a typical electron temperature enhancement within the CASP, and this is caused by very soft particle precipitation. Then this panel is showing the thermal ion imager measurement, and there are quite high velocity, ion velocity regions within the CASP region. And within those regions of enhanced velocities, we also have enhanced pointing flux downwards. Pointing flux is, of course, calculated by, it's basically this delta E cross delta P. And then we have up and downward feeder line currents, and from the magnetometer measurement, and the last panel is the broadband extra low frequency wave turbulence that is often observed, for example, within Aurora Oval. And all in all, this ionosphere-thermosphere is a very complex region. Many kinds of processes are taking place there. And there, of course, are very many open questions. I just put here a few ones. So the first one is, why does the sun and the solar wind magnetosphere coupling, or how does it drive this Earth's ionosphere-thermosphere system? How these parameters vary during storms, and what are the key drivers? How important are the small-scale structures, for example, in Joule heating, which are not always resolved by measurements? How large variations we can have in the neutral mass density affecting LEO satellite orbits by atmospheric track. And then about the future, so I was very happy to hear that SWARM is still going to continue because it has so nice measurements. Then in the future, we will have SMILE and Aurora C, and as we have heard, NanoMaxSat MMS-2, and EISCA 3D as the ground-based instrument. But all in all, this ionosphere-thermosphere region is difficult to observe. There are many complex processes, And we would definitely have more measurements than the magnetometer measurements. We would like to have magnetic, electric field, electrons and ions, nuclear densities, optical observation, everything. We need everything to understand what is going on. Then I would also say that combining ground-based observations and satellite data is essential. And also this ionosphere, we have that is now the site of quite many satellites, so it's very important for us to understand what is going on there. And we have shown that in some of our papers that even quite small storms can cause significant changes in the ionosphere-thermosphere system. But what about if we would have more extreme events like this Carrington storm in 1958? That was something we have not seen after that, or even some millennium events like this 774 AD event, from which we have only some evidence from cosmogenic isotopes. So this is my end. Thank you.